Don't even get me started on spiders. Gross. Not a fan of insects or creepy crawlies. I'm not terrified of bees, but I am terrified of large buzzy things that won't... I almost said fuck off. That won't go away. I said it anyway. Gross, yuck. Anyway, let's talk about chemistry, something that's a little less scary for some people. And by some people, I mean me. I left everybody with this problem last week, I believe. Is there a... There's not a thing after it, okay. Ah. So, just as a little review, we're going to do the second problem here that gives you a mass percentage and calculates empirical formula. And hopefully we all remember how to do that. The general gist is to turn everything into moles. And then from moles, get your pseudo formula. And from your pseudo formula, get an actual formula. But in this case, I don't give you a mass. I just tell you the percentage of some sample. So, what are we going to do to solve this problem? I only actually need this one. So we'll put that up there. Alright. So, if I have a sample, and that sample is given as a percentage, then what I can do is take any sample, say 5 grams, and times it by those percentages to get the mass in that 5 gram sample. Now, 5 grams would work here, but there's an easier way to do this, and that is instead of picking 5 grams, you pick 100 grams. Because in a 100 gram sample, if 27.29% of that is carbon, then that means that of those 100 grams, you just take that percentage, and there you go, now you have your mass. You can do the same thing with oxygen here. I'm briefly glancing at chat and I'm reading your horror stories and I'm like, I don't know if I want to be a part of this world anymore. I hate bugs. I hate them. I say that, but I end up being the brave person when I'm around my friends. It turns out a lot of chemistry faculty are like arachnophobic and I don't know why. I hate spiders, but I also hate killing them. So I'm like, no, don't kill it, but keep it away. All right, so we got to turn grams of carbon into moles of carbon because we're turning everything into moles today. My mother is afraid of bees. She's terrified of them. So when I was growing up, she would like go screaming across the yard, and I was like, "Oh, it's a bee." And like I was never bothered by bees. I've been stung by bees all the time. Much to her chagrin, my brother was in a relationship with a beekeeper for a long time. And so that was always awkward when she came over and was like, I know all this stuff about bees. And my mother was not having any of that. That person was like perfectly fine. Like she was great. But Mom did not want to know anything about her career. Oops, that's the wrong letter there. Hold on. Moles of oxygen. So I'm just going through this problem and talking about bees in my personal life, I guess, so that's fine. I mean, we did this last week, so this is all review. And I believe I even asked you guys to do this problem, and hopefully you did, so you're going to get the numbers that I have on the board here. 72.71, 15.999, 4.545. Alright. So there you go, there's the first part. I'm going to scroll this over just a little bit so I have more space. Oh, edge of the world there. Hold on. So we turned everything into moles, and the next step would be to create our pseudo formula. So that means I'm going to take these numbers and I'm going to just stick them in a formula. Even though there is no such formula that looks like this, that is okay. I don't know if these dots are visible there. We'll make them a little bigger. And then I divide by the smaller of the two numbers, which is that. So I get C is just 1. And when I do O here, well, if I could type it in the calculator, that's probably a 2, right? Yeah, I got 2.000440. That is close enough to me to say, yeah, that is the empirical formula. Remember, it's never going to be exact. It's going to be really close, though, and that's when you round. If you're, like, really close to, say, a fraction, you're going to multiply. So if you got 1.5, you're going to have to multiply your answer by 2 at the end. So that is how you determine empirical formulas from mass percentages. And we're going to do more of that today because we're going to use empirical formulas and the results of those calculations to do molecular formulas. So the next step is to take mass spec, which we talked about in Chapter 2. We're going to launch this particle through the detector, and we're going to weigh it. And let's suppose that I put a molecule with empirical formula CO2. It goes through the mass spec, and I learn that it weighs this. And there should be a dot there. Hold on, let me make sure I did the math in my head right. I might not have. I'm going to have to change that number in a second. Yeah, I totally didn't. So let's suppose that you learn that it weighs this. There we go. So I put this CO2 empirical formula through the detector, and I get a peak at 88. And you're probably thinking to yourself, well, wait a second, CO2 doesn't weigh 88. If I plug that in the calculator, I get 12 plus 16 plus 16. That's 44. So we need to differentiate between what we know our thing should weigh and what our thing does weigh. So this right here is the empirical formula. Empirical formula. And it has a mass of whatever it has in AMU. So carbon is 12. Each oxygen is 16. So I would conclude that the mass of this is 44.01 AMU. And so this is the empirical mass. This down here is whatever my molecule ends up being. It's the molecular formula. And its weight would be its molecular mass. So what I end up doing is I need to figure out how these two things differ. What I put in weighed this. What my empirical formula is weighs this. And I know that empirical formulas are just multiples of stuff, right? So, oops, that kind of turned out crappy. So this molecule could be this. It could be this. It could, oops. It could be C3O6. It could be anything in this family because they all reduce down to this ratio. And so you've probably already figured it out by now what the answer is. So what I need to do is I need to take my molecular mass and divide by the empirical mass. What is the empirical mass? The empirical mass is the weight of your empirical formula from the periodic table, yeah. So since my empirical formula is CO2, I just figure out what CO2 is. The molecular mass, you have to put in a device and it spits out a number. So I'm going to tell you the molecular mass. But the empirical mass you can calculate. So now I have empirical mass divided by, or I'm sorry, molecular mass divided by empirical mass. That's going to give me a multiplier. And I believe your textbook calls that N. And so what you do is you take your empirical mass and you multiply it by N to get the molecular mass. So in our example here, we would say, okay, the molecular mass is what does it actually weigh when I put it in the detector. That was 88.02 AMU. And this can be in grams per mole. That's fine. You can use whatever unit you want. Now I want to divide by the empirical mass. Again, any unit you want, but these units do have to match, so they cancel out. And when I punch this into my calculator, I get this as my multiplier too. So what that means is that my formula here, here's my empirical formula. I'm going to multiply it by the multiplier. That should be a times 2. Here is my molecular formula. And again, when we talk about molecular formulas, that is the actual formula of what you're putting in there. So as a molecule, you just put in this thing. And this would be like oxalic acid ion or something. So that's how we determine how to figure out the molecular formula of a compound. And so this slide walks you through that. So figure out what the molecular mass is by putting it in the mass spectrometer. Figure out what the empirical mass is by calculating off the periodic table. Use your multiplier to figure out the empirical formula. So now that you have the gist of it, I'm going to give you a problem. Actually, no, this is a little too simple for me to just give you the problem. So we'll just calculate a multiplier here, but you can do this for practice. Tell me what the multiplier is. What is N for this sample? If I know the empirical formula is CH2O, and the whole thing, when it goes through the detector, is 180. And you did that faster than I did. I'm fumbling around with my calculator like, oh, 180 divided by 30 is, But that's the right answer. So we take our molecular weight. Where's my pen here? And I divide by the mass of CH2O, which I got 30.0 something. I'm just going to do that because I only have 3 sig figs anyway. The important part is this is your formula multiplier. Previous problem, how did I get 88.02? I have to actually give you the molecular mass. So in this problem that's currently on the screen here, I have to tell you this information because you don't have a mass spec at your desk to weigh stuff. And if I go back to where we were doing this problem, that's shown right here. So everything that's in this blue polygon, I have to tell you that information. So that's not something that you can deduce or figure out without doing the experiment. Because, again, weighing molecules is really hard. And we're lucky that we have a device that we have created to do this. How much does a mass spectrometer cost? That's a great question that I don't think I know the answer to. Let's see here. Mass spectrometer, Amazon. If I wanted to buy one on Amazon, I'm getting spectrophotometers. It doesn't know what I'm looking for. So let's see here. Mass spectrometer cost. So mass spectrometers are not super expensive. And by not super expensive, I mean $200,000. Which, as far as instrumentation goes, is quite expensive. Now that's new. But yeah, $200K. That would be a lot of student lab fees to pay for that. We have a different device that we use. Yeah, it's a bit out of everyone's price range, but you know, If we overthrow the system, maybe we can get cheaper chemical sensors. I don't know. But yeah, that's how you determine that number, is you have to buy a mass spec. And we don't have one, so we're just going to tell you the number. All right, here's a much more challenging problem. The percent composition of nicotine is given as this ratio of mass percentages. Now, if I have 0.2500 moles of nicotine, which is a lot of nicotine, by the way, and it weighs 40.57 grams, that's like 75,000 cigars worth. So, determine the molecular formula. So what I want you to do, this is probably the most challenging way I can give you the problem. So I'm going to throw you straight into the deep end. And I want you to tell me first the empirical formula. And then what I want you to do is tell me the molecular formula based on this information. I'll give you a hint. Normally, I would be giving you an AMU. Remember that AMU is also grams per mole? And I have this, these things that I'm underlining here. Maybe that could help you a little bit. So I'm going to give you 5 minutes to puzzle through this. And at the very least, you should be able to do the empirical formula. So go ahead and try this. And keep encouraging and fomenting revolution in the chat, because that's important. I mean, I don't want you guys to get freaked out by this quarantine thing, that you become passive and to the world around you. Whatever. I don't know. Just get to work. Alright, just about a minute to finish up here. Yeah, sometimes the YouTube will start buffering, and your stream just kind of falls behind, and then when it tries to catch up, you'll suddenly jump ahead, like, a lot. I have the mode on this set to ultra low latency so that the delay seems to be the slowest between me and you all. So far, that seems to be working. I'm not exactly streaming like something at 4K, 60 FPS, but and now there's a cat here. I don't think they can hear you. Oh yeah. Oh yeah. I saw her peek on the mic, and I was like, "Oh, now I'm trying to get her to talk again. She just wants attention." Am I? I have to do empirical formulas though. I'm pulling out the desk tray to like hide from her, but it's not really helping. I want to do that. She's just gonna sit here and meow at me. All right, so let's figure out the empirical formula of this. Let me do this in black here. So I know that my carbon. So if I assume a 100-gram sample, first of all, then I can make the assumption that all of these are just masses in grams. And there we go. So I'm going to turn all of these into moles. So we'll do grams of carbon, moles of carbon. We'll just take care of this calculation while we're here. I'm going to punch that in the calculator in a second. Oops, that's not what I meant to do. Grams of hydrogen, moles of hydrogen, grams of nitrogen, moles of nitrogen. I'll just fill in all the numbers off the periodic table. And I think this is a 7. I can't read it from here. Yeah, that's right. I'll just do that too. Alright, so now I gotta punch stuff in the calculator. I got this up here. Actually, that should be a 3. There's that one. There you go. And so we'll make our pseudo formula from this. So C 6.163, H 8.642, N 1.233. I divide by the smallest number, which ends up being that. And so I get That should be a 5, right? Yeah. 8.642, 1.233, 5, 7, and 1. So I get C5, H7, N. Alright, so now that we know the empirical formula, we need to figure out the molecular mass so that we can use that to get the molecular formula. And so I know that a 40.57 gram sample of nicotine has 0.2500 moles. And so when I do this calculation, I'm going to have this as my units, grams per mole. Remember that you can take any two quantities and divide them together, and then you'll get that in that unit. Same as with density. So if you want to find the density of something, you take its mass and you divide by its volume, and then you get its density in mass per volume. You can figure out the molar mass of anything the same way. And this is a common question that you encounter in chemistry, and everybody forgets to do this. They're like, I don't know the molar mass. I know its mass and I know its moles. You just put them together. 40.57 divided by 0.25, so that's just that times 4. 162.28 is what my calculator says. We'll do that for sig figs. So this is my molecular mass. I need to figure out what this has for an empirical mass. And so that C5H7N would be 12 times 5 plus 7 plus 14. About 81. That's me estimating. Obviously, you could go to the periodic table and get more digits, but what's going to end up happening here is I'm going to take the molecular mass divided by the empirical mass. And I'm going to get 2. So the empirical formula times 2 becomes the molecular formula. So I take this formula, times it by 2, and I get that as my answer. And if you went and looked at the empirical formula, or the molecular formula for nicotine, nicotine, Wikipedia, then what you would find is that, let's see if I can window capture this. There we go. Boop. That's the wrong part of the window, though. I want this. I'm trying to drag this over, but it's not. Oh, that's why. There we go. That's the part that I want. There's its structure, and if I scroll down a little bit, oops, you can see that its molecular formula is right here. So we got the correct answer. And I actually used real data to do this, so. All right, so that's how we do molecular formulas. I think that's enough molecular formula practice. Oops, I can stop this timer here. So now you know how to do these. Here's another example that you have here. I will let you do that as an exercise in homework. We're going to move on to the next section, which is to talk about molarity and concentrations. Wow, we might actually get to Chapter 3 today, which surprises me. That'll be fun. All right, this is the last bit that you need to know. In the lab that's due on Thursday, I give you a very simple calculation, and then I show you how to do molarity. In that lab, I just say, oh, take the number of moles and then divide by liters. That's basically what molarity is. You've already done this in Chem 140 or in high school chem if you have taken either of those options. So this should not be anything super new. In order to talk about molarity, though, we have to talk about what a solution is. And we got to talk about some properties of solutions so that all of this has a foundation to make sense from. The first thing we want to talk about is that a solution is any mixture that is homogeneous. So this is really key right here, the homogeneous part. If you have a heterogeneous solution, we need to actually specify that, and then we need to be very careful about it. In the lab, do we have to change the liters to milliliters before doing the calculation? That's going to depend on what you want to do with it, and we'll go through a few examples here. Mostly the trick is make the units match what you want to do. We're going to mostly be using liters, but there will be other applications where you want to use milliliters. In Chem 161 through 163, most solutions that you use are aqueous. And now that I'm looking at this picture, is this a mouse right here? Like, I've never really looked at this picture very carefully. Is there a mouse sitting on top of that beaker? Anyway. I guess so. Now, when you have a solution, there are multiple components to it. The first thing that you want to consider is the solute. And that's going to be the thing that you put into your container that there's less of. The thing that you put more in is the solvent. And when you mix those two things together, you get the solution. Now, very important, there's really only one direction that you can go with aqueous solutes and then solid compounds. And that is to put a small amount of solid into a large amount of water. So generally speaking, water is going to be the solvent in almost all solutions that we deal with. But in some different specific definitions, say like air. If you take a deep breath of air around you, the solvent in that's going to be nitrogen. But if you were breathing from like an underwater breathing apparatus, like a scuba tank or something like that, the solvent might be different, depending on like what the composition is. Now, there are a bunch of ways that you can prepare solutions, and we have names that describe these. And the first thing we want to talk about is concentrated. So something that is concentrated has as much solute as it can hold. Or, I'm sorry, that's saturated. Something that's concentrated has a lot of solute in it, relative to something that's dilute. You can make something dilute by adding water. So in this diagram here, these molecules right here that are indicated, these are solute particles. And the water is the empty space between them. So a concentrated solution is just going to have more solute particles per unit volume, the volume being the part that we boxed in. And the dilute solution is going to have more water in there. I just dropped my pen. Thankfully not on a cat. She would have been like, ah! And then meowed at me. Now, you can go between these two however you want to. So, the easiest way to do this... I don't know why it says control on my screen here. Is just add water in. So you can dilute stuff very easily. Now, if you wanted to concentrate something and go the other direction... there's really only one action that you have available. And it's tedious. You have to evaporate or boil away water. If you leave a aqueous solution out on the countertop and you let the water slowly evaporate away, then you will concentrate what remains in that container. If you boil it, it will also do that, but some substances don't handle temperature change very well. and those substances might decompose. That could be an issue depending on what you're trying to do. So that's something you'll have to be mindful of in, say, organic chemistry. You could heat something and crystallize it that way, but if you do, you might ruin it. So, how do we express concentration? We're going to use the units of molarity, and molarity is kind of like density. It's a compound unit. There's 2 units, and they're not going to cancel out, and you have to keep both of them. On the top here, the units that we're going to have are going to be in moles, and on the bottom, the units are going to be in liters. And you'll sometimes see this just expressed as a capital M, and these mean the same thing. Yeah, that sounds like disaster. If you oversalt food and then you have to add water to it, and it just do, you'll never get it right again. But it is the same principle. Yeah, you can overconcentrate things. I have learned to adapt to that by just not ever thinking that too much salt occurs. Sorry, I didn't sentence that very well. I love salt. I put salt on everything. So now you'll notice here that I put in red the solution and then indicated that the volume of the solution is used for the denominator, not the solvent. And the reason for that is because if you have 2 liquids and you pour them into each other, their volumes change considerably. What we want and how we've defined molarity is the volume of the entire solution once the solution has been made. And so that has some implications here in terms of how do I write a procedure that discusses preparation of a solution of a given molarity. And let me clear this screen here real quick. That's good enough for now. And so what we want to indicate here is that when we are figuring out the molarity of something, if I put, like, say, this beaker, and it has 50 ml of, we'll say, NaOH, and I put it into this volumetric flask here, it might fill this much down at the bottom here. And then we'll say that this is the fill line. If I fill the remainder with water, and then mix really well, I can make the solution. And this is where the problem comes from. If I asked you this question, how much H2O do you need to add to fill the container? Right away, everyone's going to immediately do this. Because 50 plus 450 is 500. And then I would say that is absolutely wrong. And you'd be like, what? What the heck? So I'm going to show you a video. I got to find this video because I never know if I put this link in this class, but I think that this video is really interesting to see. So YouTube, and I want volumes don't always add up. Yeah, here we go. So YouTube video, that's the one I want. If I go like this, that is that too big? Yeah, that's too big. So, oops, let me do it this way. I think I lost part of the video here. There we go. Alright, so what's going to happen in this video is we're going to put 2 liquids together and show that their volumes don't sum like you'd think. Now this guy's gross. Literally, that's his name. His name is George Gross. There it is. I just like to make that joke. If you're watching George Gross, I think that your videos are great. What he is going to do is put these two solutions into the larger solution here. What's important to note, you can see my cursor here, is that I'm going to point out things to ensure that there's no trickery going on here. First of all, there's a 500 milliliter flask on the left and a 500 milliliter flask on the right. And then the clear one that has nothing in it currently is 1,000 milliliters. And George has color-coded each of these to show that you are actually mixing them together. When you mix yellow and blue, you should get a familiar color, and we're going to see that happen. Now, what he's going to do is he's going to fill these very carefully. The left one is distilled water, or deionized water, actually. And the way that you fill a volumetric flask is you have a mark that's on here. When the flask was first made in the production facility, a known quantity was poured into it, and then they painted this line to be the fill line. The fill line will be in a different spot on every flask because all the flasks are made kind of differently. So maybe the walls are a little bit thinner, or the diameter is a bit thicker, or whatever. So a 500 milliliters is going to come up to a different length. But they paint the fill line on afterward, and so it is calibrated to be very good. So he's going to pour some liquid in there so that the meniscus of this, and again, we're viewing it from head on, so we're going to have some error here. The meniscus will be level with this. And he's going to do this to the other solution too. But the other solution isn't deionized water. This yellow one is deionized water, but the blue one is ethanol. And you get the point. So we're going to do the same thing to this one. This is, I believe it's 95 or 100% ethanol. And he's going to fill it to the fill line. So the solutions are prepared. He's going to pour one solution into the big flask, and then take the other solution and pour that in on top of it. So here you go. There you go. And pause. So hopefully you would agree that all of the liquid was transferred from the left flask to the right flask. And that there's not much, if any, left in the first flask. Yeah, that's a mana potion. We call that ether. Don't drink ether, by the way. It does not restore your MP. We're going to put the yellow solution in here, and as you can see, the solution at the bottom turns green. Alright. All done. Yellow solution is now completely poured in here. Both flasks he poured from are empty. And when we look at how far we got, it's not even close. So the two liquids mixed together left some like 40 or so milliliters difference here. In fact, you see all these bubbles here, and as the bubbles fizz out, the liquid level is actually going to lower because the gas is displacing liquid, and it's going to condense down to be even further away. So the gas from the air that got mixed in there is not actually going to improve our result. And you might be asking yourself, well, why is this the case? Why did two liquids that have the same volume not sum together to have the same volume? And this is going to depend on if... Oops, that's the wrong... There we go, that's what I want. It's going to depend on if I could find the picture here, so... And let me see if I can get a good picture. There's one specific image that I've seen of this demo. And unfortunately, I don't know how to describe it other than like golf balls with dust in them. There's a meme out there that talks about a professor taking like a thing of golf balls and putting it on a desktop and saying, "Hey, is this full?" And everybody goes, "Yeah, the beaker is full of golf balls." So it's like this. And then here's the golf balls. They fill up the container. because you can't put more golf balls in here because the container's full. And then what the instructor does is he takes like marbles or gravel or whatever, and the little tiny pieces fill in the gaps. And then he asks, is it full? And then everybody goes, yeah, it's totally full. And then he pours in sand, and the sand fills in the gaps. And then he says, is it full? Yeah, it's full now. And then he pours in water, and the water fills in the gaps between the particles. What's essentially happening when you mix any two different liquids is that meme. So this molecule right here could be the ethanol, which is larger than the water. So if you mix two liquids, they fill a container kind of like how golf balls would fill a beaker. There's going to be some space between the golf balls, just like there'd be space between the ethanol particles. And as a result of that, molecules that are smaller will fill in those spaces. And that space has already been accounted for, and I'm using air quotes to say the word accounted, when we take the volume of something. So if I mix two things together, some of the volume that was already attributed to ethanol, the water molecules will slide into that. And so the sum of the volumes ends up being less than the result. So the takeaway here is that volumes don't add together if the solute and solvent are different. Okay? And that's an important thing to remember, because that will screw you up if you are preparing solutions in the laboratory. And it's also unclear if you provide directions that refer to volumes. So to go back to our question from before here that said how much H2O is added, we would not say 450 milliliters in this case. Even though the solute and the solvent are probably the same because it's an aqueous solution, the best way to answer this question is to say we're going to add enough to reach the fill line. And because the fill line is calibrated, you don't need to know how much you add. You just slowly add enough until you have calibrated the container. What would be the empty space? So the empty space is actually just space. Because liquid molecules will move and bounce across each other, there is actually empty space between them. In fact, between your atoms inside you, I'm using the royal you here, as in like everybody that I'm talking to, and myself included. Between all of our atoms is empty space. In fact, 99.9% of our bodies is empty space. You could condense all of your matter down into something that is really tiny. And if you did that, you would have the density of a neutron star. I just dropped my pen under the desk, so that's great. We're not going to use that for now, because we're probably going to take a break. But you'd be incredibly small. I think that you could take... I've seen this statistic somewhere. It's along the lines of you could take the entire population of, I want to say the United States, and if you compress everybody down and take out all the empty space, they'd fit in like a teaspoon. So when somebody calls you an airhead, you should say, no, I'm a spacehead, because I'm 99% empty space. There's no air there. And then you should also not be insulted, because since you understood that joke, you understand chemistry better than they do. Alright, we're going to take a break because I dropped my pen. I had to crawl under my desk to get it. So I'm going to put the title card up. Let's put the break timer up. Oh, I don't have a timer on screen, so that's not going to capture anything yet. Hold on. That's just telling me I should update. Let's start the timer. Let's start the music. And I'll see you in a bit. Darn it. One of these days I will get it. That's the wrong thing. There we go. I muted my mic. All right, so back to work here. Let's talk a little bit more about molarity and how to calculate it. Now that we know that the volume of the solution is the important component and not the volume of the solvent or any of the components that are used, we're going to note that and use that in our procedures to make solutions. And that's going to be the point of this whole section, is how do you make a solution? Write out a procedure and tell me how to do that. All right, so first example, what is the molarity of this solution with these properties? I gotta erase my diagram here so I can draw on this picture here. There we go. What is the molarity of this solution? All right, so if I want to know the molarity, first I should write down the formula. Molarity is moles of solute over liters of solution. And that's going to just be 2 moles calcium chloride divided by 1.75 liters of solution. And when I punch that in my calculator, 2 over 1.75, 1.14285, which I get to keep 3 sig figs, so 1.14. And then I got to write the units that are left over. Well, nothing cancels, so I get to keep everything. So moles calcium chloride per liter. Now, the solution is implied, so it's usually dropped. But another way to write this would be something like this, moles per liter, and then you put the formula over here. And then finally, one last way to write this is you just write a big capital M afterward. Now, you'll notice in every case that I have this identifier attached to it. That's really important. When you're giving the molarity of a solution, you need to tell me what the molarity is, because you can't have a molarity of something and it just be water, for example. So like if you said something is 10 molar what? It's got 10 molar HCl, 10 molar sodium chloride, whatever. You got to tell me what it is. Okay? And that's important. Just because we want to be as clear as possible when we are making those descriptions. Oops, I didn't actually click on that. There we go. All right. Now, some useful applications with molarity is that if you take the formula and you rearrange it a little bit, you can get units out of it that may be helpful in other applications. For instance, if I take molarity being moles per liter, and I multiply by the volume used, you'll notice that the liters cancel out, and what I'm left with are the moles of the solute that were used. So if you need to figure out, like, say, stoichiometry in Chem 162, you take the molarity of a solution and multiply it by the volume that is used to determine the amount of content that is in there, or the number of moles, how many particles. Let's do this example, and you'll notice that I'm asking you for grams here, which is specifically not what I just described. But we know how to get from grams to moles, so we could do a calculation like that. And we'll do that in this problem. I can't tell if that's chopped off at the top. Let me just do that. All right, so how many grams of this are in this solution? So if I have my molarity formula, so molarity is moles per liter, and I times both sides by volume, I'll get M times volume equals moles, so M times volume equals moles. And my solution is 2.80 moles of what? Sodium chloride per liter. and I used this many liters of it. So when I punch this all into my calculator, I get 0.840 moles of NaCl. Which I then can turn into grams because we know how to do that. So in a mole of NaCl, I will have some number of grams of sodium chloride. And I want to say that it's this. I hope that that's right. Let me look it up on Lentech. Could be 58. I don't actually remember. I'm just doing lazy math here. NaCl. Oh, 58.44. Okay. There we go. And so that's the molar mass of Na and Cl added together. 58.44 times 0.840. 49.09. And I only get 3 sig figs, actually, so I gotta do this. And since I have sodium chloride, I gotta identify that that's what that is. And there you go. That's how you solve the problem. So in a third of, or not a third of a liter, I'm sorry, in 3/10 of a liter of 2.8 molar solution, there'd be almost 50 grams of salt in there. Oops, there we go. All right, I got more problems for you to try. So I want you to, oops, we're going to skip that apparently. Never mind. Let's go back. I want you to tell me the molarity of each of these solutions, and we'll go over the answers in just a second. These are pretty straightforward calculations, so shouldn't take you too long to do them. I'll say 6 minutes. All right, good luck. We're all counting on you. I had to sneeze there. That's why I muted. But yeah, good luck. just a little more time to finalize those answers. I'm going to go fill my water. And then when I get back, we'll go over them together. All right. Let me do this. Delete. All right. So let's answer these questions. What's the molarity of this solution? So the first thing we need to know is the formula, which we have, moles of solute over liters of solution. Now I need the moles of the solute, but I've been given a gram, so that's unfortunate. That means more work for us. I can turn grams into moles, though. And 1 mole, there are 101.10, looks like, according to Lintech. 101.10. All right, so this number, as written, would give me my number of moles. So I could hit enter and just go on. But what I'm also going to do is I'm going to do this. Molarity is moles per liter. So I'm going to take the volume of the solution. I'm going to put it on the bottom here. And I'm not going to put anything on top because this is just 1, right? Because I'm supposed to divide by the volume, so I'll just do that as a multiplication. But I don't have the right units for my dimensional analysis, so what I'll do is I'll do this. And in a milliliter, there are 10 to the minus 3 liters. So now, when I do all this multiplication, I will get molarity, because it's moles of solute. The moles of solute part is in blue here. And then the bottom here, liters of solution, that's this red part. And when I punch all this in the calculator, I get 35.96 over 1.5808, which I get to keep how many of these? I get to keep 4. 1.50. Oh, that wasn't 0. 8, 1. There you go. That's the answer. What mass of HCl is contained in 0.5 liters of 14 molar HCl? So for the second question here, I know that MV equals moles. And I can turn moles to grams. So I'm going to start by taking the molarity. I'm going to multiply by the volume. So that's MV equals moles. And now that I have moles, I can then say mole HCl, grams HCl. I want to say that something like that. MV is mass time or molarity times volume. That's the answer I got for that. So a thing that Canvas cannot do is it can't do sig figs, which is really frustrating when I'm in a class where I'm supposed to be evaluating all of your answers for sig figs. On the quiz, what I will do is I will tell you, please report your answer to this many, at least this many sig figs. And the reason for that is because when I set the bounds for the answer on the quiz, I give you a little wiggle room because maybe you have a rounding error from the source of periodic table that you got or something like that. And then that would affect your answer. So if the question asked you 1.581 was the answer, and you put 1.579, I want you to be able to get credit for it and not be marked wrong because, oh, you chose a periodic table that the last digit was 8 or something, or you had too many sig figs and it rounded higher or whatever. So if your answer was that number, 1.579, on a quiz where the answer was 1.581, I would mark it correct. I would program it to be marked correct. But if you rounded it to, say, 1.6, then you would actually be outside of the bounds of the accuracy that I set. And then it would mark it wrong. So when I ask you solve for this many sig figs, it's so that I'm ensuring that you land within the bound of the accuracy barrier that I'm trying to set up. But as far as like which periodic table should you use, how many sig figs should I use off of that periodic table, etc., it shouldn't matter too much. Because the last digit in your answer is always going to be a rounded digit. And if you're off by 1 or 2, I still count it, and it should fall within the bounds. Oh, I thought I bumped my water. I bumped my calculator. Not as important. Okay. Can I get this last problem in here? Let's see. What volume vinegar contains this much massive solute? Okay, so we need to solve for volume this time. So molarity equals moles over volume. So I could rearrange that equation to say volume equals moles over molarity. But I don't know the number of moles. I do know the number of grams, so we'll start with that. So I have this many grams of vinegar. And I know that this is vinegar because I wrote the problem, but you could just write HC2H3O2. It's the same thing. So grams becomes moles. This would get me my moles, which would go up here. So I'll figure out that number. 60.06. That one I actually thought I had memorized, and it was right. So, oops, I just wrote the wrong thing, though. All right, so this would give me units of moles. But then I'm going to divide by molarity, so that means I'm going to do this. And then I'll just put the molarity on the bottom. So you can see that these problems are starting to become less like, oh, let's follow a pattern, and more, oh, I need to plot out how do I get to what I'm doing using these formulas that I've been given. And so the answer I got was 0.3973 liters. Oops, dropped my calculator. There we go. So those are some molarity practice problems that we can do. Make sure you are proficient on calculating molarity and transforming from one unit to another, because there's a whole bunch of different ways that you can do that in this class. I will probably ask you all of them on the Chapter 6 quiz, so it's good to know. All right. I think this might be the last thing that we have time to do today. If I'm looking at my clock correctly. Actually, maybe we'll have a little bit more time after this. How do I prepare a solution in the lab? What is the technique to make a solution properly so that you can get a reproducible, homogeneous result every time? And the way that we're going to do solutions is we're going to do a 3-step process. And the first step is always figure out what you got to put in the beaker. The second step is always fill the rest of the way with water. And then the third step is mix 50 times. So step 1 is going to be the calculation part. And we're going to do that, which is basically what we've been doing all along. Now we're just going to put some procedural stuff to it. So let's suppose that you want to make this solution. I want a 1 molar solution of NaCl, and I want a 1 liter quantity of it. How do I prepare that? So first of all, you got to put in the amount of salt, or sodium chloride, that you calculate. And you'll see that right here, 1 mole NaCl is 58.44 grams. To make a 1 molar solution with a volume of 1 liter, you would need 1 mole. So you dump that in, and then you add enough water to dissolve all the solid, and then you keep adding water until you hit the fill line. I don't know why I used the mouse to draw that, but that's okay. So it's hard to see, but this is the fill line right here. And once you have hit the fill line, you have a 1 molar solution. But that 1 molar solution will not be homogeneous. That 1 molar solution will have most of the salt at the bottom. So this is the last step that you have to do, and this is actually really important. If you don't mix your solution and you start collecting data samples with it, then what ends up happening is that if this is the true value of your solution based on your calculation, and you just start pipetting stuff out from the top and then slowly reaching to the bottom, what you end up with are things that look like this. The first ones are going to be really dilute because it's all water. The salt hasn't had a time to migrate up that far. The last ones will be really concentrated. And that's obviously no good. If you're going to do the same experiment every time, it's got to be the same solution every time. And that's going to be critical when you're doing things like the Beer's Law experiment, which I believe is probably next week's lab assignment. I'm not sure. I had to look at the schedule. All right, so what I want you to do is to use that 3-step plan that we said earlier to make this solution. First thing you got to do is you got to figure out how much KBr you got to weigh out. So that's going to be step 1. So step 1 is weigh out whatever your stuff is. Step 2 is going to be to add enough H2O. And then you tell me. And then what was that most important part? That's step 3. Write out a 3-step procedure. Do the calculation, and then write that out. Now we'll get back to you in just a second. Alright, that should be enough time. So let's go over the answer. Oops. Alright, first things first, we need to figure out how much of our solid to put in the container. That is not what I want. Why are you doing this? Oh, because it's holding control again. Okay. There we go. Okay. So in order to figure out the mass of KBr, I need to figure out the moles of KBr, which I can do by taking m times v equals moles. So I will take the molarity, KBr, per liter, times the volume, and actually, you know what I'm going to do. That will just give me an answer in moles, but I don't want moles. I want grams. So I'm going to try and cancel this out by putting this down here. That should be at grams. No idea what the molar mass of this is. 119 is what it looks like. And according to calculator, 416.5. I get 3 sig figs, so there you go. So that's the first step. Figure out what the mass of the solution is. So we did that. Now we need to describe in words or pictures how to do that. And so whenever I ask you to do this, which obviously won't be often because I can't really make you do that on the Canvas quizzes super easily, you would just write out the 3 steps. So step 1 would be weigh 417 grams KBr and we gotta put it somewhere. Where should we put it? In the garbage? Put it all over the pizza? No, don't do any of those things. You're gonna put it into a 1 liter flask, and you're gonna specifically use a volumetric flask. And the reason for that is because those volumetric flasks that we were showing have very precise volumes, like we showed in the demo where we wanted to add the volumes together, but they didn't. All right. Step 2, we're going to put water in it. How much water do we put? We're going to add H2O until it reaches the fill line, or the mark, or whatever you want to call it. We're not going to report a specific amount of volume. Don't tell me how much water I'm supposed to put in there. If you tell me a volume, that's an error. That is not ideal. Because what that's saying is, okay, I should go get some glassware, specifically measure out this volume of water, pour it in there, and ignore the fill line, which is not what you want to do. Then step 3 is you're going to mix it really well. Generally speaking, the safe way to do this is to invert it 50 times. That takes you about a minute if you just rotate it once a second. And that should be enough. There is a secret step 4, and that is to enjoy. All right, that's how we make any solution. We're going to now do a liquid solution, and that'll probably be it for today. We can finish chapter 6 on Thursday and begin the horror that is quantum mechanics. All right, so let's talk about diluting. When you dilute solutions, shaken, not stirred. That's correct, yeah. Step 5, profit. Sure. If you can sell this stuff, absolutely. When you have solutions that are very concentrated, sometimes you don't need that concentration to be that high. And this is useful because you can make a lot of solution from a concentrated stock. Water has an obnoxious property that it takes up space. So, for instance, if I have like a 20 molar solution, and I only need to make 1 molar solutions, I could just take 1/20th of what I need, and then make the rest water, and then it will be the correct molarity. And so this is called dilution. So adding water to concentrated solutions makes them dilute. And there is a formula for this, but very important. And I'm going to write this on the screen here because every student who's in the first year messes this up. This formula is for dilutions only. So when you are thinking about chemistry and you think, oh, this formula, it's super easy, everybody remembers the formula. But you have to take the second step, which is, okay, I'm going to sit down and think about what I'm doing. Am I making a dilution? And if the answer is no, do not use the formula. A lot of the time people will try and throw this at a titration. Don't do it. Remember, dilutions only. Titrations are not dilutions. On the board here, I'm going to put a bunch of words. And then I'm going to try and put them on this screen so that we can see them. That'll have to do. Because what I want to do here is... So I have plenty of space here. Okay, so if I have a bottle of this stuff, so this is my stock solution. There's the handle, I guess we'll say. And we'll say, okay, there's the label on it, and there's tons of the stuff in here. We're going to take a sample of that, and we're going to put that into our volumetric flask. That wasn't very good. Hold on. I don't know why there's this delay between my tablet and my writing. And also, good job at me for putting the arrow and pointing it at where it needed to go. And then we're also going to put H2O in there too. So on our description here, M1 is going to be the concentration of the stock solution. So this is M1 right here. V1 is going to be the volume of stock solution that was used. So it's not the volume of the bottle, because we don't care about that. We're not going to use any of it. Or all of it, I should say. But whatever we take is going to be the volume that goes in V1. Now we can look at V2. That color might not be dark enough. There we go. V2 is the volume of the flask that you are creating your solution in. And then M2 is going to be the molarity of the solution at the end of your procedure. Now, generally speaking, anything that I'm going to circle in red here is a fixed quantity. So this is fixed. That is written on the bottle, and you cannot change that number, provided that you didn't spill it or evaporate it or concentrate it or whatever. This number right here, you're going to choose what you want that to be. And this number right here, you're also going to choose what you want it to be. Because you can make whatever solution you want. I could make 1 liter of it, or maybe I want to make 10 liters because I'm making the batch for all of the labs in the college today. Ultimately, the amount that I choose for my final molarity and final volume is going to affect how much I need to prepare that. So that means that this last quantity right here, V1, this is what you're going to calculate. And I realized that I just went behind the thing here, so there you go. So you're going to calculate V1 in any of these preparation questions. Now, I could give you a question where you don't actually calculate V1, but that would not be a prep question. That would be some other question. That would be something like, what volume do I need to dilute this in order for it to be this molarity? That would not be a prep question. That would just be a knowledge question. So let's do a prep question like this. Suppose I have 10 molar calcium chloride in the stockroom. I need 3 liters of 0.5 molar calcium chloride. What do I do to make this solution? So let me clear my diagram here that I just drew. That is totally not useful in any way. Hold on. There we go. All right. So this is a dilution. That means I should write down the formula. I should write down the formula correctly. And what I need to do is I need to identify my components. And so what I'm going to do is I'm going to do something like this. All right, so I need to figure out what M1 is, M2 is, V1 and V2, and whatever in my diagram. So I have 10 molar calcium chloride in the stockroom. It's in the stockroom. That means that it must be my stock solution, which is 1. So I'd write, I'm on the eraser. There you go. I'd write that. 10 molar. M2 would be what I want to make. That has been decided in the problem already. V1 is the amount that I need to use, and V2 is the amount that I want to make. Well, it says there I want to make 3 liters, so my solution will have a final volume of 3 liters, which means that this is what I'm solving for, like we expected, because it's dilution. So let's solve this equation for V1. That's going to be M2, V2, M1. And we'll plug in all the numbers. That's not the right number. Hold on. Sorry. I confused myself. So M2 is 0.500. V2 is 3 liters. And M1 is 10 moles per liter. So that's where that went. These cancel. Oops, I missed. There you go. These cancel out. And I'm going to punch this all in the calculator. 0.5 over 10 times 3. And I got 0.150. And then the last question is, what are the units of this problem? Well, it's whatever's left over. There's my leftover unit. So that's what this is. So this problem says to prepare the solution in this way, we have calculated that we need to acquire 0.150 liters. Remember that this is V1. What is V1? V1 is the stock solution. So I would need to acquire 0.15 liters of stock solution. And when I write my procedure out for my 1, 2, 3 steps, step 1 is going to be pour that volume. And this was 10 molar calcium chloride into a 3-liter volumetric flask. So that's step 1 of our preparation. Again, step 2 and 3 are going to be exactly the same as before. So step 2 would be add H2O to fill line. Lost an I in there, that's okay. Step 3, mix 50 times, and enjoy. And there you go. That would be the directions on how to make this solution. And so that looks like this. Pour 0.150 liters of the solution into the container. Use the water to rinse it down into your container because you want to make sure you get all of it. Then fill with the fill line until it's done. Yeah, you don't want to drink that. When I say enjoy, I mean like enjoy it for its color. I don't know if I would enjoy this color personally. All right, so for this last example, what I want you to do is I want you to try, 2 out of 10, would not drink again, yeah. I want you to try and calculate this dilution, and then write the 3-step plan to make that preparation. So here are the directions that you want. Give this a try. While you're doing that, let's talk about grades for lab number 1. I am not fast when it comes to grading. I actually read your labs. I believe that the speed, because I did some of this grading last night, and I'm also preparing other content at the same time, and I can't do them both at once. I believe the speed at which I can grade your labs is I can do about 12 an hour. So that means one class of 24 takes me 2 hours or so, if I'm not distracted, which is unlikely. Last night I did about 2 to 3 hours was how long it took me to do 24. I have 72 of these to do. So the answer to the question, when will we get our labs back, is kind of, unfortunately, whenever you get them back. I'm going to do the best that I can to grade them quickly, but it does take time. And that is, unfortunately, a luxury that I don't really have, because prepping all of the other stuff takes a lot of time. That being said, I have graded Section C had their labs graded, and I can tell you the average score was about 18 or 19 out of 25, I think, which is pretty good. I'm going to grade Section A. I'm going to try to grade Section A later today. I'll grade Section B tomorrow, probably, and then I will upload all of them at the same time. So I won't be able to get them to you until they are all done. If I sent you an email, and I realize these people might not be watching, if I sent you an email that said, hey, you sent me an invalid format, you need to send me the valid format within 24 hours, or else you don't get credit. Make sure that if I sent you that email yesterday, you do that tonight, because that is when I need it. Otherwise, you got to use your NQA coupon. And a little early in the quarter for that. Starting with Lab 2, I am restricting file types. If you try and upload something that's a PDF or an OSL or something like that, because you chose the wrong option, it will reject it, and it will tell you your file upload failed. So make sure that you are uploading the correct file type, XLSX only, and there shouldn't be any problems. Yeah, you don't really want to enjoy HCl. Hopefully everybody got that number. I'll give you another minute or so to do this. We'll go over the answer, and I believe that that's all I have to do. There's going to be a bunch of stuff flashing by on the screen. I'm just checking really quickly. Okay, yeah. So there's not much left to do here, which we will finish on Thursday. I used to be able to just like hold Control and or Alt and scroll out, but it doesn't seem to let me do that on this version of PowerPoint that I have. I am using ancient technology here. What version of PowerPoint is this? 2003. So, yeah. The software I am using is older than most of you because I got it for free in grad school and I never, I kept the install disk. Alright, let's go over the answer. Oops, I didn't clear this. Deleted. Most people probably don't get that reference either. So I personally find that if I have lots of information in a problem, making a little matrix to put all that information in is helpful. You do you. If you want to make like an ordered list where you do this, I wrote the same thing twice, but that's okay. And you just write them out in a list, that's fine, but I like doing it this way personally. I just like tables. Alright, so stock room is 14 molar HCl. I want to make 1 liter of 1 molar HCl. And just like most of these types of problems, we're going to be solving for V1. So that's going to be 1 mole per liter times 1 liter over 14 moles per liter. You'll notice that I'm not writing out moles per liter every time this time. And that's because the molarity on top and the molarity on bottom cancel out. If you did write moles per liter, you might be tempted to cancel this liter with this liter, and then that could get confusing. And so I got this. So that is the volume of stock solution, which is 14 molar HCl. So for our prep, we would say add this many liters of 14 molar HCl. You could also have written it like this. 71.4, oops, not liters, milliliters. That volume is also okay. Where do we put it? Do we put it in the sink? No, that would kill all the fish. We're going to add that to a 1 liter volumetric flask. Why 4 sig figs? Did I write 4 sig figs? There should only be 3 there. 0.0714 is 3 sig figs. Those zeros are placeholders. So we put it in the flask. We're going to fill with H2O. To the fill line or the mark. Then we're going to mix it really well and enjoy. And we're going to enjoy it as much as you can, HCl. That's okay. Making mistakes is part of learning. There's our procedure. So I'm going to leave these problems on the next slide for you, to practice. And some of these may be a different type of problem. They're not dilution preparation. I've tried to like word them in different ways to try and hide what they are doing. But if you interpret them carefully, then you'll realize which of these 2 problems is just the problem we've been doing all along, and which of these 2 problems is actually the different problem. Okay? So these types of molarity and concentration questions are what you're going to see on the Chapter 6 quiz, because that's kind of all I can ask you in Chapter 6. Is just, hey, dilute this thing. Hey, dilute this thing. how many moles are in this thing. And pretty straightforward. There will be some conceptual stuff too. And of course, there will be the other mass percent stuff that we're doing at the end. Something to note in the very end of this section, we're not going to do the Chapter 7 balancing equations. That will not be on part of your assessment. So the plan is to finish Chapter 6 on Thursday. That is it for today. Please make sure that you are reading ahead on Chapter 3. Chapter 3 is really scary. I'm going to emphasize that as much as I can on Thursday. That Chapter 3 is where shit gets real. I believe I've said that before. Make sure that you aren't coming in blind, because we're going to spend like 3 or 4 weeks in Chapter 3. So there's not going to be a lot of quizzes, and then all of a sudden there's going to be 3 quizzes at the end, because Chapter 3 is that long. And Chapter 3 is really difficult, because it's all new stuff, it's weird, and stuff. That's really all I can say about it. I want to thank everybody for coming out. I'm going to leave the screen up very briefly while the dad joke plays out, I guess. I don't know. This better be good. If I'm leaving the stage open for your joke. I can see people are already leaving. We're done for the day, by the way. You don't have to stay for the dad joke if you don't want to, but I figure we might as well put it on air if it's good. Yeah, you're gonna leave us hanging like this? I mean, there's really only one response that I have to that, and that is... yeah. Thanks for coming to lecture. We'll see you next time.